Hey guys, so we are going to finish up chapter 4 today. There's only 4 sections in chapter 4 that we cover in this class. So today we're going to do 4.4, which is all over exponential and logarithmic equations. So the previous 3 sections have really prepared us for this section. The first one was exponential, the second one was logarithms, then it was, dealing with their, like how to play with them, their properties. And so now we're going to combine all of that so that we can actually evaluate exponential and logarithmic equations. We can solve. We haven't really done a lot of solving. We've done a lot of condensing or expanding or simplifying, but we haven't done a lot of solving. So today we are going to solve. So how do we do that? Well, the first thing to note is that if you are solving exponential equations, if you can get the bases the same, so that you have b raised to some power equals b raised to a different power, then you can just negate the bases and just set m equal to n. So that is the easiest way to solve exponential equations, is getting the bases to be the same, because then you can ignore the bases and just compare the exponents and solve for the variable that is within the exponent itself. And so there's kind of 3 steps that you do if you're able to do that with your exponential equations. You rewrite the equation as b raised to the m power equals b raised to the n power. So you get the same bases on both sides. Then you ignore the bases and you just compare your exponents by setting m equal to n. And then you solve for the variable that is remaining within those exponents. So we're going to do 2 examples. Obviously, you can see the examples because I have my notes pulled up, but I'm going to work them on the board so that you can hear me talk through the actual steps of how we come to these conclusions. So for A, we have 2 to the 3x minus 8 power equals 16. So on the left, we have a base raised to an exponential power, but on the right, we just have a number. And so this is one of those situations where we say, can we write the number with the same base? Can I write 16 with a base of 2? If you're not sure, because you're not sure of your powers and things like that, well, we know the base needs to be 2 if they're going to have the same base. So I'm going to make a short list over here of 2 to different powers to see if I can write 16 as the base of 2. So 2 to the first power is 2, 2 to the second power is 4, 2 to the third power would be 8, and then 2 to the fourth power would be 16. So I can write 16 as a base of 2. So I have 2 to the 3x minus 8 equals 2 to the fourth. Now I have the same bases, and so I can ignore the bases and just set the exponents equal to each other. So I have 3x minus 8 equals 4. Add the 8 over, and 3x equals 12. Divide both sides by 3, and I get x equals 4. So I was actually able to solve for the variable within this exponential equation. Let's look at B. B, we have 27 raised to the x plus 3 equals 9 raised to the x minus 1. So both of those have the number base with exponents in the with variables, but neither of those have the same base. So we need to think, is there a common base that we could write these as? And the answer is yes. 3 can go into 27 and 3 can go into 9. If you write over here to the side, 3 to the first power is 3. 3 to the second power is 9, and 3 to the third power is 27. So we're able to write both of these numbers with the same base of 3. So instead of saying 27 to the x plus 3, I'm going to say 3 to the third times x plus 3, because we'd have a power raised to a power, which means we multiply those exponents. I do the same thing on the other side. I have, instead of writing 9, I'm going to write 3 squared, but then I still have that times the x minus 1. So now I can forget the bases and just set my exponents equal to each other. I'm going to distribute that 3 in, and I'm going to distribute that 2 in. So I have 3x 9 equals 2x minus 2. I'm going to subtract my 2x over because I have 3 of them on this side, which leaves me with x plus 9 equals negative 2. Subtract over that 9 and I get x equals negative 11. So I was able to write all of those with the same base. And that makes it really nice because then we just ignore the bases and set the exponents equal to each other. But that's not always going to happen. We're not always going to have nice numbers that have the same bases. So if you can't get the bases the same, we're going to use logarithms to solve. This is kind of where all the other sections from chapter 4 are coming together so that we have all the tools necessary to solve these problems. So how do we do that? Well, here's your steps for solving exponential equations using logarithms. First, you're going to isolate your exponential equation or expression. So you get it by itself on one side of the equal sign. If you have a base of 10, you'll take the common log to both sides. If not, then you'll use the natural log to both sides. So you'll be using the natural log a whole lot more than you'll be using the common log because you can only use the common log if you have a base of 10. If you have the base of any other number, you're going to use the natural log and you'll natural log both sides. Then you're going to simplify using different rules. So if you have ln of b to the x, you're going to use your power rule to bring that x out front. If you have ln of e to the x, remember that's base and what you're logging is the same, so those go away to where you're left with just x. Or you'll have the common log of 10 to the x, again, your base is the same of what you're logging, so that goes away. And then we're going to eventually evaluate or solve for the variable. We will get this all the way down as far as we can, and then sometimes you'll be asked to find the equivalencies. And what I mean by that is you'll actually type it into your calculator and you'll get something with a decimal. The problems will be very specific on if they want you to leave it in log form or if they want you to find the equivalency and round it to 2 decimal places or something like that. So make sure you read your instructions on your problems so you know exactly which form and which way they want you to put this in. This is also true for on tests and on the final. You always want to read all of the instructions so you know exactly which format to write it in because you won't get full credit if you write it in the other form. Okay? So let's do some examples where we are solving and we're not going to be able to get the same base. And so we're going to have to use some of our other tools that we've learned. We're going to solve we're not logging yet. We're going to solve 4 to the x equals 15. 4 and 15, we can't get those to have the same base at all, so this is where we're going to use logarithms to solve it. Notice that 4 is not 10. That doesn't have a base of 10, so we're not going to common log it. We're going to ln both sides, okay? So when I say ln both sides, I literally mean ln. We're going to write ln of 4 to the x, or 4 raised to the x power, equals ln of 15. Remember, the whole goal in this is to solve for our x. We are actually solving. So I'm going to use the power rule to pull that x down front of our ln of 4 equals ln of 15. Now, x is multiplying right here, x times ln of 4. So if I need to isolate my x, I'm going to divide both sides by ln of 4. And that'll give me x equals ln of 15 over ln of 4. This is where you need to know what type of answer your problem is asking for. If it wants you to keep it in log form, then this is as far as you would take it. If it wants you to actually get a numerical answer where you're rounding to 2 decimal places, you would type ln of 15 into your calculator and divide that by ln of 4. And that is equivalent to 1.95. Okay, we're going to do a couple more examples of this. So that's how you do the first one. The second one is 10 to the x equals 120,000. We do have a base of 10, so we will common log this one instead of natural logging it like we did last time. So I'm going to log both sides. So log 10 of x equals log 120,000. Power rule lets me pull that x down front. Log of 10 is log base 10 of 10, which means it goes away. That means I have x times 1, which is just x, equals log of 120,000. So if it wants it in log form, that's all you do. If it wants the numerical equivalency, then you type that into your calculator and you get it's equivalent to 5.08. So we logged both sides, did the power rule, simplified, and got our equivalency. That's why we always want a common log if we have a base of 10, because it's going to go away. It's going to simplify out to 1, which is really nice for us. And I am going to show you C right there on the bottom of the notes, just in case you can't read it right there. So obviously you can see a little bit of the work, but that's okay. So C says we have 40 times E. Remember, E is the irrational number that we have. E to the 0.6x minus 3 equals 237. Don't let all of the e's and the exponents with the variables and all that kind of stuff scare you away. We're solving these just like we have done every other equation that we've encountered all semester long. So step 1 of our list said to isolate our exponential expression. Well, it's not isolated right now because we have this 40 attached, we have this minus 3 out here, so we're going to get it by itself first. I'm going to add that 3 over. So I have 40e to the 0.6x equals 240. This 40 out front is multiplying, so I'm going to divide both sides by 40. E to the 0.6x equals 6. Since I have the base is not 10, I'm going to ln both sides. So I have an ln of e to the 0.6x equals ln of 6. Base is the same as what, like it's ln is base e of e, so that leaves me with 0.6x equals ln of 6. That goes away to 1. I'm still solving for this x, so I'm going to divide both sides by that 0.6, which gives me ln of 6 divided by 0.6. Again, if that was as far as they wanted you to take it, you'd be done there. Or you type it into your calculator and you get 2.99. So we had to do some algebra first to isolate our expression. We had to add over the 3, divide by the 40, then we ln'd both sides. Ln of e is 1, so we were able just to look at 0.6x by itself, divide by the 0.6 and solve for our x. Last one like this. We'll scroll up so you can see it. D says 5 raised to the x minus 2 equals 4 raised to the 2x plus 3. We can't get common bases. We can't get 5 and 4 to have the same base. So what I'm going to do is I'm going to ln both sides. Neither of those have a base of 10, so I'm going to ln, and there'll be ln of 5 to the x minus 2 equals ln of 4 to the 2x plus 3. Now, I'm going to use my power rule to pull these powers down front. So I have x minus 2 times the ln of 5 equals 2x plus 3 times the ln of 4. Now this one's kind of a mess because we have x's on this side and x's on this side. So we're going to have to do a little bit more algebra than what we've done in the past. First, I'm going to distribute this ln of 5 into my parentheses so that I have x ln of 5 minus 2 ln of 5. And I'll do the same thing on this side with my ln of 4. I'm going to distribute it in. So I have 2x ln of 4 plus 3 ln of 4. Now what I want to think about doing is I want to get all of my x's to one side and everything else to the other. So I'm going to subtract this 2x ln of 4 over here, and I'm going to add this 2 ln of 5 over here. I'm going to move them around. So if it has an x, it's moving to the left, and if it doesn't have an x, I'm going to move it to the right. So I have x ln of 5 minus 2x ln of 4 equals 2 ln of 5 plus 3 ln of 4. Okay. Now if I look at my left-hand side, I have x ln of 5 minus 2x ln of 4. So they both have that x in common, so I'm going to factor that out. So that'll be x times ln of 5 minus 2 ln of 4 equals 2 ln of 5 plus 3 ln of 4. Now, if I need to get x by itself, I have x times this stuff inside the parentheses. So I just divide both sides by everything in the parentheses. So it looks like a long mess, but I can still do it because it's just x times it. So I'm going to divide that over. So I have x equals 2 ln of 5 plus 3 ln of 4. All of that is going to be divided by what was over here connected to my x, which is the ln of 5 minus 2 ln of 4. And you're like, man, that's a mess. It is, but we are doing algebraically what we can in order to simplify it. If you type all of that into your calculator, you'd get that that is equivalent to negative 6.23. So the extra steps that we had to do was the fact that our exponents both had an x on it. So we had to distribute our ln's in and move all of our ln's around so that the ln's that had x's were on the left, the ln's that didn't have x's were on the right, and then we could pull out the ones that had the x so that we could then solve for x. So that one has a little bit more algebra than the other ones that we've done, but it's all stuff that we've been able to do just with regular numbers. Now we're just doing it with logarithms as well. Okay, so that's how we solve exponential equations. When we can't get the bases the same, we use logarithms. So now what if we have logarithmic equations? Like we start with logarithms. Well, you're going to rewrite it so that you just have one logarithm, log base b of m equals c. Then we're going to use this saying that, and you're going to hear it a lot. The base becomes the base and the answer becomes the exponent, so that we can change from a logarithm over to an exponent. So the base of our logarithm becomes the base of our exponential. The answer of our logarithm becomes the exponent of our exponential, and then that equals what we were logging in the first place. So log base b of m equals c becomes b of c equals m. We then solve for the variable, and we'll have to check our solutions because we only want to keep positive solutions. Because if you remember back to 4.1, when we first started talking about exponential equations have to be positive. You can't raise it to an exponent and get out a negative answer. So we are only wanting to keep the answers where m is positive. If you compute up any others where there's negatives or there's 0, then we have to get rid of those solutions. And that'll make a little bit more sense as we start actually working through these. Let me slide down. I can probably do 2 of them without moving. Okay. And I'll scroll so you can see the first two down there. Okay, so we're solving these, and these are logarithmic equations. We have to convert them into exponentials in order to solve them. So we have log base 4 of x plus 3 equals 2. So the thing to remember, and the thing I'm going to repeat over and over again, is base becomes the base, the answer becomes the exponent. So the base of this logarithm is 4, so that becomes our base. The answer is going to become our new exponent. So the answer was 2, so that becomes our exponent. So it's 4 to the second power. And then everything that we were logging, it becomes our new answer. So that's x plus 3. So we went from log base 4 of x plus 3 equals 2 to now 4 to the second power equals x plus 3. So that is 8 equals x plus 3. We're going to subtract that over, and that'll give me 5 equals x. Oh, excuse me. I was like, what is wrong? What's wrong is I don't know that 4 squared is 16. I hope you guys were yelling at the screen. 4 squared is 16, and you subtract 3, you're going to get 13. So why is my answer so different? The last step on our step says to check our solution. We want to make sure that it works and it's true. So you have log base 4 of 13 plus 3 equals 2. I'm just plugging it back up into the original equation. Log base 4 is 16 equals 2. Base becomes the base. The answer becomes the exponent. 4 squared is 16. We're good to go. That one checks out okay. Let's look at B. We have 3 times the ln of 2x equals 12. Well, the first step is we want to make sure that our ln or our log is completely isolated. Right now it is not because we have that 3 out in front. So I'm going to divide both sides by 3. So I have ln of 2x equals 4. Now I have it isolated. So I'm going to do base becomes the base and the answer becomes the exponent. So what is the base of the natural log or of ln? Well, the base of the natural log is e. So we have e to the 4th because the base becomes the base, the answer becomes the exponent, equals 2x. X is not isolated. We'd have to divide both sides by 2. So e to the 4th over 2 equals x. As weird as that looks, and even though it doesn't give you a nice number, that is a solution. If your problem tells you to round to decimal places, then you'd actually enter that into your calculator and solve it. But for the most part, e is a number, so you're allowed to leave it like that. It's like using pi. You can leave it as pi whenever you have it. Just to save board space, I'm going to show you, I did check it here. Where we plugged e to the 4th in, we get 4 equals 4. We're good to go. Okay. Let's do a few more of these. I'm going to do 3 more actually, it looks like. We have log base 2 of x minus 4 equals 3. We already have it isolated, so base becomes the base. 2 to the 3rd. Base becomes the base, the answer becomes the exponent, equals x minus 4. 2 to the 3rd is 8, x minus 4. I'm going to add that 4 over, and I get 12 equals x. If you went back in and plugged it in, it would work. Again, just for time and space, I'm not going to do that, but it does hold true. All right, let's do a little bit harder. Let's do one that's going to make you think a little bit. We have log base 2 of x plus log base 2 of x minus 7 equals 3. Well, I don't have a single log. I have more than one log. So we have to combine these or condense these using our rules that we learned in the previous sections, where we have our product rule, our quotient rule, and our power rule. Since we have log base 2 of x plus log base 2 of x minus 7, that plus tells me I can combine those two logs, since they have the same base, using the product rule. So I can write this as log base 2 of x times x minus 7 equals 3. I'm able to condense them in using the product rule because they have the same power, or the same base. Now I can continue on just like I have before, where the base becomes the base and the answer becomes the exponent. My base is 2, so that becomes my base. My answer is 3, so that becomes my new exponent. And then everything I'm logging will become my new answer. So I'm going to go ahead and distribute that x in so that I have an x squared minus 7x. Well, I'm going to go ahead and subtract over this 2 to the third power, which is 8, so that I have 0 equals x squared minus 7x minus 8. Then hopefully you all are sitting there thinking, that looks a lot like a quadratic. It's because it is. You guys have done this in chapter 1, you've done it in chapter 2, and now here it is again in chapter 4, because it doesn't go away. So if we're solving for x using quadratics, then we need to factor out, like we need to factor this. Or you would use the quadratic formula. I recommend factoring. It's usually easier. So x squared factors to x and x. This negative sign in front of the 8 tells me I'm going to have a negative and a positive. This negative in front of the 7 says I need a lot more negatives than I do positives. So I need factors of 8 that add together to give me a negative 7. Well, the factors of 8 are 1 and 8 and 2 and 4. 2 and 4 are not going to add up to give me 7 at all. But if I had a negative 8 and a positive 1, those would give me a negative 7. If I'm still solving for my x's, then I have to set each of these equal to 0. So x minus 8 equals 0, and x plus 1 equals 0. So I get x equals 8, and I get x equals a negative 1. Now here's where you would be checking your solutions by plugging them in to make sure that they're okay. This is where we have to test to make sure all of our answers are going to work. If we look back at our original problem, notice this first term is the log base 2 of x. Well, log base 2 of 8, that's fine. That's going to give us a number. But when we take the log or the ln of a number, we can't take the log or the ln of negative numbers. It doesn't work. So that means we can't take the log base 2 of negative 1. This doesn't work. And this is what that step meant when we need our answers to be greater than 0. Our answer here is not greater than 0. So that solution doesn't work. So the only solution that we would actually get for this problem is the x equals 8 solution. Okay? You cannot have logs of negative numbers. And I say that in here, right here for you, with a little hashtag or star or whatever. All right, last example. Okay, we have the ln of x plus 2 minus the ln of 4x plus 3 equals the ln of 1 over x. Again, we don't have one ln or log, so we're going to combine on the left-hand side as much as we can. We have the ln of x plus 2 minus the ln of 4x plus 3. So that minus tells you you can condense those using your quotient rule. So that'll become the ln of x plus 2 over 4x plus 3 equals the ln of 1 over x. Now you may be thinking, okay, so do I have to subtract this over and do a whole bunch of other stuff? Actually, you don't. There's a nice little rule about this. If you have the log base b of m equals the log base b of n, so you have two logs that equal to each other and the only thing that's different is the m and the n, then you can ignore the bases and just look at your m and your n. Kind of like we did earlier when we had the exponentials in the same bases. We could ignore the bases and just look at the exponents. We can ignore the logs and just look at what we are logging. So we don't have to worry about this ln and this ln. We can just say x plus 2 over x, 4x plus 3 equals 1 over x. So that's pretty nice. I like that. I like that I don't have to deal with those ln's anymore. But now what do we do? Well, we still need to solve for our x. And the way we're going to do that is we have a fraction equal to a fraction. So you can cross multiply. That's where you're taking x plus 2 times x and 4x plus 3 times 1. So x plus 2 times x will give me x squared plus 2x equal to 4x plus 3. I'm going to subtract everything on the right-hand side over, so I want to try and get a quadratic again that I can solve. So I get x squared, and then I'm subtracting over my 4x. So it'll give me a minus 2x, and I'm subtracting over my 3, which gives me a minus 3. Now I'm going to factor this quadratic. X squared gives me x and x. This negative in front of the 3 tells me that I have a positive and a negative. I need the factors of 3 to add or subtract to give me 2. Well, luckily the factors of 3, there's only 1 and 3. And I need more negatives than I do positives, so I need a negative 3 and a positive 1. I'm going to set each of my terms equal to 0, just like I did on the previous problem. So x plus 1 equals 0, so x equals negative 1. X minus 3 equals 0, so x equals 3. And again, I need to test these points to make sure that I'm going to get a positive solution up here in my ln's, because that's the problem. The problem isn't necessarily that I get x is negative, because earlier we had x is negative 11, and that one didn't cause any problems. The problem is when I type this in to my problem, am I going to get ln of a negative number? Well, ln of negative 1, if we look right here, ln of 1 over x, if x is negative 1, then that's ln of negative 1, which does cause a problem. So that one doesn't work. If I put 3 in, that's ln of a third, that's fine. If I put 3 in here, that's ln of 5. If I put 3 in here, that's ln of 15. So that one doesn't cause a problem. So the only solution then would be x equals 3. But again, it's not necessarily that the answer for x was negative that caused the problem. It's that when we plug it in, we're taking the log or the ln of a negative number, and that is the problem. But that is also the end of 4.4 and the end of chapter 4.